Oggie's coming in to talk about concentration of solutions. And that doesn't surprise me because the concept of concentration, solution concentration, is deceptively tricky, especially with regard to the difference between the concentration of a solution and the amount of solute in that particular sample of solution. There he is. Oggie, come in. Thanks, Prof. Sit down. Having trouble with the idea of concentration, I can do any number of calculations, C equals N on V, and get them all right, but I just don't feel that I'm understanding what I'm doing, why I'm using those equations, and how to apply them, when to apply them. They're sort of not making sense to me. Okay, good. Let's forget about equations for now, do your calculations. Let's try and think about visualising solute molecules in solution and try to understand what's going on in solution and then see if that helps to understand the equations. Yeah, you always go on about visualisation, Prof Bob. Always. Well, there's good reason for that, Aussie, as I hope you'll come to see. If we're visualising things, we can give meaning to the words that textbooks have. Textbook wording can't really give you the sense of what's going on in solution that visualisation can. Some terminology, you know that if we dissolve some sucrose in water, we would call the sucrose a solute, the water the solvent, and the homogeneous mixture that results from dissolving one in the other is the solution. I'm going to stick with talking about solutions of sucrose in water. And that's because it's a relatively simple system in that the sucrose molecules in the solid, when we dissolve them, they still stay as sucrose molecules. We don't have the complication that other things do, you know, the ones we call electrolytes. The molecules break up to form ions. This doesn't happen here, so we'll stick with the simplest of systems. Now, in trying to visualise what concentration means, think about concentration is just how crowded are the solute molecules in a solution. How far apart are they, is what I like to try to think about. So for example, at peak hour in the mornings, the traffic on the freeway is very crowded. We might say that the cars are highly concentrated. Okay, the cars on the freeway are crowded together. We say that's concentrated. So I guess in a concentrated solution, the molecules of solute are relatively close together. Exactly. And the word that means the opposite to concentrated is dilute. Exactly. The closer the molecules are together, on average, the more concentrated solution. The further apart they are, the more dilute a solution. There's no dividing line where we could say this solution is concentrated, this one is dilute. It's just a relative thing. Things are more concentrated or more dilute than another one, or the same concentration. Now, the most common way, the way that we're going to talk about, let me start again. Solutions, concentrations of solutions can be measured in a number of different ways. We're going to use the one that's called molarity. And the units of that are moles per litre. And if I had a solution in which the concentration is 1.00 moles per litre, what would that mean to you? Well, I guess that would be a solution in which you have 1.0 moles of solute, maybe sucrose, and 1 litre of water. Well, no, on two counts. One, I didn't define that we had 1 litre of solution. It could be any volume. Concentration is regardless of volume. But let's say we're talking about 1 litre of this solution. It's not made by 1 mole of solute and 1 litre of water. In fact, it's 1 litre of solution, not of water. So, for example, when you're making a solution like this, and I have here, in fact, it does turn out to be 1 litre of solution, I might have made this 1 mole per litre solution, 1 litre of it, by dissolving 1 mole of sucrose into some water, shake it up, stir it till it's all dissolved, as you've done in the lab, take it up to near the mark, mix it up, and then bring it up to the mark, and we should have 1.00 moles per litre. The reason that's different from 1 mole of solute and 1 litre of water is that the solution now has the added volumes of solute and solution, but they're not additive, and the molecules of sucrose can actually bring the water molecules closer together, a sort of contraction of the volume that they occupy. So if we actually added 1 mole of sucrose and 1 litre of water, it wouldn't come exactly to that mark. It'd be something less than that, in fact. Okay? Our way of measuring with molarity is the number of moles per litre of solution. Okay? Now, we can write that as the concentration is 1.00 moles per litre. And if we put a label on that bottle, it would be 1.00 mole per litre aqueous sucrose solution. Aqueous because it's in water, and could be in any number of other solvents like alcohol, for example. It's not, it's in water. Okay? Prof, I thought we used capital M for molarity. Lots of bottles in our lab have got a capital M on them, not moles per litre. You're right, and those labels were made before I came here. Not that there's anything wrong with capital M, it's a shorthand way of representing molarity. But when you're doing some calculations, you're very much aided if you write out this in full, because then you can see what the units are, which ones cancel, and you should finish up with the right units. You can't do that with a capital M. Okay? Now, I should emphasize here that when we're talking about concentrations, we're not really talking about the concentration of a solution, we're talking about the concentration of the solute in the solution. And the best way I can make that point, I think, is if we had a solution in which there are 2 solutes, A, which is 1.00 moles per litre, and B, whose concentration is 0.50 moles per litre. Now, it'd be wrong to describe this as a 1.50 mole per litre solution. Well, not wrong, but it's not really descriptive of the system. The system is a solution in which the concentration of A is 1.0 moles per litre, and the concentration of solute B is 0.50 moles per litre. Okay? And if that were the case, I hope you can visualise that the molecules of A in this solution are closer together on average than the molecules of B are. It is more concentrated in A than it is in B. That makes sense? The A molecules are closer together on average than B molecules are. Just how close are they? Lovely, lovely question. We can calculate it pretty easy. If I have a 1.0 mole per litre solution, I have in there number of moles of solute is, suppose I had 1 litre, is 1.0 moles, and the number of moles of solvent is, I've got 1,000 mils, 1,000 grams approximately, divided by the molecular weight, 18, that's 55.5 moles. And then the relative number of moles is the same as the relative number of molecules. So for every molecule of sucrose, there'd be 55 molecules of water on average around it. Yeah? So a reasonable distance between one molecule of solvent and the next. And if the concentration was 0.1, let's say, moles per litre, it would be 1 to 550 make that moles of water for every one of the solute. So they're not that close, but still closeness is concentration. Aha! 1/10 the concentration of that, so the molecules are 10 times further apart in this. Great, great. You can see that. Aha. Good. Now I just want to do a couple of experiments, let's say, with you. A couple of little tasks, thinking tasks. I've got here an aqueous sucrose solution. I knew it was coming, so I made it up. 0.50 moles per litre. Okay, I'm going to give you a couple of tasks with that. Now, Prof, that doesn't look like 1 litre, it looks like a lot more than a litre. Maybe 2 or 3 or 2.5 or something, I'd guess. You're right, but concentration is independent of volume. Right? It's a bit like density of a substance is the mass per volume of a sample of the substance. It doesn't matter how big the sample is, the ratio of mass to volume, the number of grams per litre stays the same. And equally, the point I've been trying to make is regardless of whether we have 17 litres or 0.013 of a litre, the concentration could be 0.50 moles per litre. The volume of a given concentration just is determined by the amount of solute in that. So for example, this solution here, if I had, let me have a look here, if I had 1 litre of it, that's not 1 litre, it's more, but if I did have 1 litre of it, the and it is, the concentration is 0.50 moles per litre, then the number of moles in this 1 litre is concentration times volume would be 0.50 moles per litre times 1.0 litres. Per litre and litre cancel out, and we have 0.5 of a mole. 50 of a mole. Okay, so I might just remove that for a while so we can see. If I had 10 moles, 10 litres, you'd find that I'd have exactly the same concentration if I had 10 times that, 5.0 moles. And if I had 0.1 of a litre, I'd have the same concentration if dissolved in that were 1/10 of that, 0.05 of a mole. 10 times the concentration, 10 times as much solute to have the same concentration. Okay? Yeah, I'm getting it. The concentration is a number of moles per litre, regardless of whether we have 1 litre or not. The same concentration, if we have 10 times the volume, we must have 10 times the amount of solute. Or I could say that in a number of different ways. Okay, good. Now I'll put this back again, and I'm going to do a couple of things and give you a bit of a thinking task, a couple of thinking tasks. Some containers, and let's call this a measuring device, 1 coffee cup full. And let's, for the purposes of conceptualization, regard my measures as equal. 1 coffee cup full into there. And into this one, 1, 2, 3, 4, 5. Now, what are you thinking? Well, Prof, I guess this is what we just talked about. These are both samples of the same solution. So even though they're different volumes, they must have equal separation, equal crowdedness, if you like, of the solute molecules. They're just different volumes of solutions of the same concentration. So if this is 5 times the volume of that one, then there must be in there 5 times the amount, number of moles, or the number of molecules, as there are in here. Yeah? Confident about that? Good, good, good. Let me empty these out and do something else. One, 2. 1, 2. We've got equal volumes of the same solution. Okay, nodding away, all right. Now, I've got about 200 mils in there. Now I'm going to add water. This is not a sucrose solution, this is now water. Okay, now what are you thinking? Well, there's more of this, there's got to be more solute in this one than in this one. Oh, sorry, Prof. Hang on. What did you add? Water. So before you added the water, you had equal volumes of the same solution, so they had equal amounts of solute in them. So now you've added just water, we haven't added any more solute, so the molecules in here of solute, of sucrose, must be further apart on average than in here, sort of 5 times more spread up, dispersed than in here. This one is now more dilute than that because it's got the same number of molecules in a bigger volume. Exactly. Let's do a calculation here. I need... Yeah, in the first instance, our concentration is 0.5 moles. I think we should cross off that 0 moles per litre. And the volume is, say, 200 mils. So I took 2 of those coffee cups fulls. So the volume, 200 mils, is 0.2 of a litre. So the number of moles of sucrose is C times V is 0.50 moles per litre times volume litres. Litre and per litre cancel out, and so I've got 0.10 moles of solute in here. Since I haven't added any more to here, I just added some water, I must also have in the second one, let's call this 2. Firstly, secondly, also got 0.10 moles. But the volume is now, let's say, that's about 1 litre, 1.0 litre. For purposes of discussion, let's presume it's 1.0 litres. Now the concentration is N on V is 0.10 moles divided by 1.0 litres. This is 0.10 moles per litre. Firstly, you see the value of writing this out in full when you're doing calculations and not having capital M. Now, can you see that we've diluted 200 mils up to a litre, it's a factor of 5, and the concentration has come down by a factor of 5, from 0.5 to 0.1. Yeah, we've made the same number of molecules further apart by diluting them, by the same factor of their volumes. You know, Prof, I think I'm getting to see this better as a result of visualising the molecules in the solution. I think that's helping me a lot. I didn't realise before how good it is, how powerful it is to visualise the system at what you call the submicroscopic level. Great. Yeah, I'm glad that Aussie's come up with this recognition, because I do think it's one of the most important factors, visualisation at the molecular level, one of the most important factors in our understanding of chemistry at the macroscopic level, the things that we can see and touch.